Hello everybody, and thank you for the opportunity to present our work. My name is Andreas Klinger, and the presented results are joint work with Ulrike Meyer. Consider the following problems. People trying to find a suitable job, and companies trying to find a suitable applicant. Using online portals to find suitable dating recommendations, or if you want to participate at an online auction, or finding a rideshare on the fly. All these problems require private information, like preferences or the current location, that should be protected. For one-shot evaluations of these problems, there are already privacy-preserving techniques. However, these problems are actually continuous. That is, they are actually online problems and not one-shot computations. So, for example, applicants or passengers arrive over time and leave if they are not matched. In this talk, we will first show how to solve such online problems in a secure and privacy-preserving fashion. In the first part, we present a new model for privacy-preserving online algorithms, and then we construct a distributed protocol that implements this in a secure and privacy-preserving fashion. In the second part, we will discuss a new view with respect to what ideal is. Let's start with the general setting. Assume a group of people with private inputs wants to compute a function over their inputs, for example, possible job matching. In an ideal world, we have a trusted third party that can be used. It receives the inputs of the parties, computes the function over the inputs, and distributes the outputs. If a fixed set of parties wants to evaluate a function over multiple rounds, they can just provide input multiple times. Here, the trusted third party should keep some state which depends on previous inputs and outputs, and the output itself depends on the state. For example, who is already matched. For these computations exist secure protocols that evaluate the function in a distributed fashion without the help of a trusted party, so-called secure multiparty computation protocols, or short SMPC protocols. However, many problems are not static and new parties arrive during the evaluation. Also, some parties might want to leave after a couple of rounds. Such problems are online problems and are typically solved with an online algorithm. Here we see the main model of an online trusted third party that can securely evaluate online algorithms with parties joining and leaving. These problems have not yet been considered in the context of secure multi-party computation. For clarification, offline or reactive protocols assume that parties are known in advance, the parties participating at the computation know each other, and typically the parties do not change over time. Here, with an online trusted third party, we assume that the parties are not known in advance, nor do the parties know each other. In addition, parties leave and join during the evaluation, so the set of participating parties changes over time. How could an example evaluation of such an online algorithm in the ideal world look like? At first, there's only the trusted third party present and no other party. In order to model the arrival of parties, we introduce a new entity called the creator. The creator creates parties and lets them join. The parties can then evaluate a single event and obtain the first output. In the next event, for example, a new party is created and joins the evaluation. And after that, in a third event, a party decides to leave the evaluation, and so on. As an adversary cannot know which parties will be created, the creator decides who will be corrupted, and corrupted parties are then controlled by the adversary. For the secure multiparty protocol, which we will be presenting in the next following slides, we can prove perfect security for a semi-honest and a malicious adversary that could strictly less than 1/2 or 1/3 of the parties respectively. A semi-honest adversary follows the protocol specification but tries to learn some additional information based on what he has seen. A malicious adversary additionally can arbitrarily deviate from the protocol in order to learn private information or even influence the output. We then say a protocol is secure if the adversary can perform the same attacks in the ideal world with a trusted third party as an adversary can do in the real world when the execution is done by a distributed SMPC protocol. In other words, an adversary cannot do more harm than what he could do with a trusted third party. Let's briefly start by repeating the concept of online algorithms, as this is what we actually want to evaluate. In general, an online algorithm receives events on the one side, for example a new input, and then has to immediately make a decision how to handle that event, that is, compute an output. For example, which parties should be matched. This process is repeated over time and continues until the algorithm is stopped or no events arrive. Internally, an online algorithm uses a function to map an event to a decision. We will call that function a decision function. In addition, the decision typically depends on an internal state, which itself depends on previous events and decisions. So, an event arrives, the online algorithm has to compute a decision with a decision function, and based on the current state, it outputs a decision and it updates the state. This is how online algorithms work in general. Now, with respect to secure multi-party computation, an event corresponds to a party arriving and providing their input, and a decision corresponds to the outputs of the parties. Note, not all parties need to obtain output. For example, it could be one party obtains output, several parties obtains outputs, or even no party obtains output. Those parties that have arrived or joined the computation and not yet left are the parties that are actually participating during the evaluation, so they're actually performing the computation. This set of parties changes over time and is not fixed nor known in advance. To keep track of who is participating, we use a bulletin board, but for the sake of this talk, we ignore the details regarding that. You can just imagine a room where the parties meet in order to perform the evaluation. Everyone inside the room is participating and all other parties are not. Who joins entered the room and who leaves the room has basically left the computation. Now, to perform the computation securely. The computation of the decision function itself can easily be replaced by a standard secure multi-party computation protocol that works with a fixed set of parties, because during the evaluation of one single event, the number of parties does not change. For such offline problems, there are already many secure protocols available, and what one actually wants to use depends on the actual decision function and the application where it should be used. So that's good, there we can reuse previous results. Now, the state needs to be available over multiple events, so we store the state secret shared among the participating parties. And in order to access the state, these parties then provide the state shared as additional input to the offline SMPC protocol to securely await the decision functionalities. So compute the outputs and update the state, which is then again shared between the participating parties. And if we repeat this process for every event, then we actually are evaluating an online algorithm. What we have left out here is that we actually require a special ramp-up phase for the first 3 or 4 parties, depending on whether we have a semi-honest or malicious adversary. What this special ramp-up phase does is basically internally simulate how the first n events would be processed by a trusted third party, and then we switch to the actual protocol here. In our paper, we have proven the security of the previous protocol, and thus we have a nice feasibility result, namely that any online algorithm can be computed perfectly secure. Note that the presented version assumes a single input per event, but in the full paper we show how to extend this to arbitrary array. This means parties can arrive, leave, provide input multiple times, multiple inputs at the same time, multiple parties arrive at the same time, and so on. In addition, proactive security is possible to achieve. That is, the set of corrupted parties can change during the evaluation of a single event or multiple events. But dishonest majority is only partially possible, as if we assume a dishonest majority and the only honest party leaves, then we have only malicious parties, and therefore we need to be careful how to deal with these situations. However, the main result of our paper is that any online algorithm can be computed securely and privacy preserving in the above model. Now, let's move on to the second part of the talk. The ideal model we presented so far follows the standard assumption of the classical SMPC setting, except for the arrival of parties. But we actually asked ourselves whether this model is actually ideal, or can it be more ideal? So what we did is introduce an ideal online trusted third party that hides everything. And with everything, we mean everything. This means especially the participant parties do not see each other. They do not know who else participates or how many parties participate. In the full paper, we actually introduced 4 different flavors of online trusted third parties with different degree of privacy. For 3 of them, we have constructed protocols improving their security. The one previously presented is the weakest one, but the most easy to grasp, so we presented it here. And actually, those 3 models use the ideal online trusted third party from this slide, which then explicitly broadcasts additional information. For example, it broadcasts when a party arrives with its input. The ideal online trusted third party, which hides everything, is the strongest one, which we will consider in the following and compared to the previously presented one where the arrival is public. Therefore, a warning. The ideal model we discuss hides everything. This means it is not known who participates, when parties join or leave, or when or if parties provide input. This is different to previous settings where it is always assumed that this is known, so the parties can somehow see each other. So we think this model is essentially the holy grail of trusted third parties, but also probably not achievable. In order to see what we could gain with such an ideal online trusted third party, consider the following example of online maximum weighted bipartite matching. At first, we have 3 managers which are looking for employees. In the first event, the first applicant joins with its preferences, 1 indicating highest and 3 indicating lowest preference. As no manager is already occupied, it is matched with the first manager. Now, a second applicant arrives with its preferences, his highest preferences. The first manager is already matched, so it is matched with its second preference, the third manager, and so on. Now let's go back to the first match. With public arrival and assuming the first manager is matched, the manager knows the other managers are unmatched, as this is the first applicant. So he immediately learns that he was ranked highest. However, if the arrival is hidden, the manager does not know how many other managers are matched, and thus does not learn whether it matched because it was ranked highest or higher preferences were already occupied. So here we have partial input leakage with public arrival. Note there are similar examples for offline and reactive functionalities. Now, does this hold for all problems? Previously, a manager could be matched only once. Now let's change this so that the matching algorithm allows a manager to be matched multiple times. If we now consider that any manager is matched, we immediately know that this manager was ranked highest. However, this is the same in both settings, so we have no additional input leakage, but sadly this holds only in the semi-honest setting, and of course the usefulness of such an algorithm is arguable. As public arrival can leak additional information, the question rises whether we can hide it. One idea is to introduce fake parties, so hide a real party inside a mass of fake parties. Sadly, this does not help, and as of now it seems impossible to hide the arrival of parties perfectly. To sum it all up, we have first introduced a new online trusted third party that allows to model any online algorithm, so an ideal online functionality for any online problem. Second, which is the key take-home message, any online algorithm can be computed securely and privacy-preserving. Third, we have seen that hiding the arrival can provide additional privacy, but seems hard to achieve. Therefore, in the future, we plan to introduce new models with better privacy and construct corresponding secure protocols. In addition, we want to further investigate how to hide the arrival of parties. Thank you for your attention, and I'm happy to answer any questions.